All right, I would like to thank the organizers that that's actually the talk in the seminar, and so the topic of this talk is surface quotient singularities and the bigness of the Cotangent bundle. This will become more concrete what this means as the talk progresses. This is joint work with my students Johannes Asega and previous student Michael Weiss. The work in this talk, originated in some sense 16 years ago when I worked with Fedia on resolutions of nodal hypersurfaces in P3, and there was the first time where the phenomenon that's going to be discussed today was proved or discovered. It's the impact of singularities in bigness of Cotangent bundle of the resolution of the surface with the singularities. We'll see later, if we arrive there, that smooth hypersurfaces in P3 do not have symmetric differentials. Symmetric differentials is an analytical object that's used in particular to obtain constraints on the existence of special subvarieties on a variety of general type. Here, let's call surface of general type. In particular, if you have a symmetric differential that is giving us an algebraic differential equation restricting the existence of rational curves, elliptic curves, and even entire curves on the variety. So abundance of symmetric differentials, which is what bigness is of Cotangent bundle is all about, gives strong constraints on the existence of rational elliptic and entire curves. The conjecture, so let's now move. So let's just remind us. So, well, in this talk, the topic is the objects that we're going to analyze are surfaces, smooth projective surface, and singular ones with quotient singularities. The Cotangent bundle is said to be big if the asymptotic growth of the number of symmetric differentials is as large as it can be. So it grows like m cubed. Well, bigness of the Cotangent bundle is a birational invariant. We also have that, of course, that if the Cotangent bundle is big, that implies that the canonical bundle is big. Therefore, the surface has to be of general type. So this talk is about surface of general type. Well, you could ask, why do we care about bigness? Well, there are several geometric consequences, but the one that originated my interest in this topic is the Green-Griffiths-Lang conjecture, which says that if you have a projective variety of general type, then this variety has, or supposed to have, a proper subvariety Z, such that any entire curve of Y is contained in this proper subvariety Z. Entire curve is images of non-constant holomorphic maps from C to Y. That's here, but it's supposed to be Y. Okay, so if you have a rational curve, you have an entire curve. If you have an elliptic curve, you have an entire curve. So this is stronger condition than just conditions on rational and elliptic curves on Y. So the connection between bigness and the Green-Griffiths-Lang conjecture is a result of McQuillan from '98, saying that if I have a smooth projective surface and the cotangent bundle is big, then the surface satisfies the Green-Griffiths-Lang conjecture. So this talk is not going to be about consequences of bigness. We could do it. There'll be another talk. Consequences like result of Macmillan. It's going to be more about criterions and understanding when a surface has big cotangent bundle. So it's more about the property of being big that we're going to concentrate and understand. And I think these talk's results are really crystallize our understanding of when does a surface have a big cotangent bundle. All right. So let's try to understand what could be criterions for the cotangent bundle to be big. So X is a surface of general type, because we know that we can restrict to this group, because bigness cannot be obtained in any other class. Well, if I want to understand, so I'm trying to understand these limits. So I want to understand how the number of Smith differentials grows as m goes to infinity. So, well, a way to understand the dimensions of space of Smith differentials, we use naturally Riemann-Roch. So I want to use Riemann-Roch to understand this, and we have a very important tool, which is Bogomolov's vanishing, that tells me that H2 for symmetric powers of the cotangent bundle is going to vanish if m is bigger than or equal than 3. This is the consequence of stability of the tangent bundle. We'll have some more remarks later on, depending on how much time we have to go deep in those remarks or proof of a result later on. All right, so if I use these two things, I obtain the following fact, that H0 is equal to H1 plus the topological expression that gives the holomorphic Euler characteristic of the sheaf. All right, and if you look at the topological part, we look at the symptotic piece, realize that the topological description of the Euler characteristic, the m cube coefficient, is given by the second second number of x divided by 3. All right, second second number is a shell number, which is the difference between the square of C1 with C2. Now, it's clear from here that we get the simplest criterion for bigness, which is the criterion, which, since the topological criterion, this just has to do with the second second number of the variety. And it's clear that if this second second number is positive, the cotangent bundle is big. All right? But this is not this is a good criterion. It is easy to check, but it's not a birational criterion. Remember, like bigness is a birational property. You should have a birational criterion coming from the topological criterion. You know, can you have it? And well, let's notice something. When I blow up a surface, the second number decreases by 2. So if I imagine I have a birational class of surfaces for which the cotangent bundle is big. Like if I have such a class and I pick up a surface, say the surface has big cotangent bundle, if I start blowing up this surface, the surface I obtain, the blow-ups, still have big cotangent bundle, but the second number will be eventually negative, right? So this is a way to create examples of surfaces with big cotangent bundle where the second number is negative. Well, a way to correct that, to make it a birational invariant, a birational criterion, is instead of doing the second number of the surface you start with, you do the second singular number of the minimal model of that surface. If that one is big, then that means that the second singular number, that means that the Cotangent bundle of X min is big, but that also means the Cotangent bundle of X is big. All right, so this is a bidirectional version of the criterion. And okay, all right. So this is the simplest criterion. Okay, if you look at the expression, this expression here, and you're taking the limits divided by m cubed, you get since what we could call the full criterion of bigness, like bigness of the Cotangent bundle happens when the sum of the second number of the minimal model of X divided by 3 plus the contribution from H1. I mean, in a sense, the H1 contribution here is what's more mysterious, more delicate. The topological part is quite robust, invariant under deformation, but this component from H1 is delicate. It depends on the formation. If you deform your variety, this component is gonna change. This limit that I have here is gonna change. I'm gonna note this limit by H1 omega. So in a sense, the asymptotic H1. Let's call it asymptotic H1 of X. And I evaluated, of course, at X min because I want to have this criterion to be a bidirectional criterion. Okay, so this is, of course, the full criterion, and of course, the difficult part is, as I said, is to understand what is this asymptotic H1. We're going to define later on like two components of the sense of the asymptotic H1. One is the local component, L H1 local component, and the non-localized component. I mean, conjecturally, and I think it is true, the asymptotic H1 is equal to the sum of the localized component and the non-localized component that we define later on. We know that we will know that this is true if the canonical model of my surface has only AN singularities, but everything indicates it's going to be true for all in the general case. So the goal of this talk is so bigness now. For us to understand bigness, we have to understand this asymptotic H1 that I handle on this, and okay, and as I said, I have two components. I'm going to understand. We have the localized component. The localized component is co-localized because we're going to see it's localized at the singularities of the canonical model. And then you have the non-localized component, for which, so this talk is really about the, in a sense, about the many results of this talk are about the localized component of the asymptotic H1. Okay. So and as I said, I say here, it's localized because it's concentrated on the singular points of the canonical model of your surface. As you know, if I have a surface general type, I have a unique canonical model. So the canonical singularities of the canonical model are invariants, bidirectional invariants, and information about this variety, these singularities are bidirectional invariants of my variety. And these singularities encode information about the localized H1, asymptotic H1. Canonical surfaces, canonical models of surfaces are surfaces with canonical singularities. In particular, these are quotient singularities. And so these are orbifold surfaces. And so I need to say, I need to state and understand several results about orbifold surfaces and orbifold vector bundles. Okay, all right. So orbifold surfaces are surfaces. For us, it will be surfaces. Well, we only consider normal surfaces, so surfaces with isolated singularities. And these singularities being orbifold surface means the singularities are quotient singularities or log canonical log terminal singularities, if you prefer that language. And so, but this is a very simple geometric description. These are quotients of a smooth germ by a finite subgroup of SL to C, which is small, meaning that fixed points of the action are of codimension at least 2. And if I have a germ of quotient singularity, I have associated with 2 natural kind of maps. One is the smoothing, which relates the quotient singularity with the germ of the smooth surface, and I have the minimal resolution. All right. One is a finite map, other one is a birational morphism. And okay, here I repeat. So we'll be looking at normal orbifold surfaces, and that means that the surfaces are quotient singularities. Okay, so for surfaces, okay, there's a notion of orbifold vector bundle, but I'm not able to save time. For surfaces, orbifold vector bundles coincide exactly with the category of reflexive sheets on Y. That's not true in version 3, but so for us, orbifold vector bundles are we're going to think about them as reflexive sheets. We are interested in the following reflexive sheets on a variety. Okay, let's just set up some natural notation. A surface is a regular piece, the complement of the singularities, and it's naturally embedded into the surface Y. The orbifold vector bundles we are interested in are the cotangent bundle, orbifold cotangent bundle, which can be which is defined as the push forward of the cotangent bundle on the regular part of the surface. We have the canonical bundle, and that's again can be thought as the push forward of the canonical bundle in the regular parts. This is going to be it's going to be a Q-line bundle. That now, of course, the objects of our talk are the symmetric powers or the reflexive symmetric powers of the cotangent bundle. So again, you can see it as the push forward of the symmetric power of the cotangent bundle on the regular part. But now there's several important relations. This is also equal to the symmetric power of the cotangent bundle double dual, because the symmetric power of the cotangent bundle does not need to be reflexive. All right, so this is not the symmetric power of the cotangent bundle on Y. You have to do the double dual. I mean, it's again we have to do with this when you do tensor operations on reflexive sheets to guarantee that they're still reflexive. We have to do the double dual of the normal operation. All right, and then we have the important for us will be Serre duality. It's the normal. It's what we'd expect. So I'll not say much about it. We're going to be used later on. Just have to be sure that you relate HI with H2 minus I by going from the sheaf to the dual of the sheaf tensor with the canonical line bundle, but then you have to do double dual again. All right. Okay, let's leave it like this. All right. So this is kind of the basics of orbifold surfaces and orbifold vector bundles. Now we are going to talk about understanding. So as I mentioned here, our talk is about understanding the localized part. So I know for what I said here, I didn't prove it yet. This has to do with H1s concentrated on the singular points of the canonical model. So I need to understand that. So local H1. So say I have a minimal resolution of a germ of a quotient singularity, surface quotient singularity. Then I can set up H1XM, which is like the local H1 at X. So it's the H1 of the symmetric power of the Cotangent bundle on X. This is our germs, these are neighborhoods. You can think about it as an affine neighborhood of singularity, which only has that singularity. Or, you know, there's this relation, this H1 is something as H0 of this sheaf here. And the sheaf is a sheaf on the singular surface, but it's concentrated. The sheaf is concentrated at the singularity. Okay, that's why it's localized, it's concentrated at singularity. Now we define the local asymptotic of H1 of X to be the lim inf of these H1s. Lim inf because we don't know if lim exists. I mean, I suspect it exists, but we don't have the proof for all quotient singularities. We have the proof that this limit exists for AN singularities, and I strongly believe that it exists for all quotient singularities, but we don't have the proof for this. We didn't go that direction. So now the localized part is still well, it can be called our definition of localized part. Localized part is going to be the sum of these local asymptotic H1s at each singularity. So when you think about the localized component of the asymptotic H1, it is this contribution given by the singularities, by these local asymptotic H1s for each singularity. Is there any questions? Okay, so we would like to, I mean, we like to get a hold of how can I find these local asymptotic H1s. I mean, these are invariants of the surface singularity, and by the way, these are unknown invariants of. I mean, no one had said them before. Invariants of surface singularities. They have been calculated for nodes. It started with work, my work with Fedya, where we had an error in the calculation. This then was corrected by a student of Fedya. I mean, the calculation is trivial. It was an error, for sure, but it wasn't. There was a mistake, and so for H1 is known, but it's not known for any other singularities. And as you're going to see below, we did it for all AN singularities, going from nodes A1 singularities to the general case is serious. Is very different problem. I mean, it's in a sense you could say that part of the setup is the same, but it's extremely different, particularly to get the general form and so on. I mean, it's a completely different animal. All right, so how do I find this asymptotic local H1? Well, we have to do, well, I guess we could try to do it directly, but I don't know how to do it directly. I don't think anyone knows. So we go indirectly. We set another definition. By the way, these definitions of H1X, XM, and so on, I mean, they're not this way, but they follow work of Wall in the 92. Practice ideas from 92. So this H0 measures the dimension of measures kind of how many symmetric differentials exists on the resolution of the surface away from the exceptional locus. How many of these, or understanding how many of these extend to the full resolution. So it's symmetric differentials away from exceptional locus versus symmetric differentials on the full exceptional, on the full resolution. Okay, and Okay, so this dimension is a finite. It's finite, by the way. It's good. And then Euler related these two numbers, h1 xm and h0 xm, and call it a name. It's called the local Euler characteristic of the sheaf reflexive symmetric power of the Cotangent bundle of X. And now there's now several relations that have to do with how we find the Euler characteristic of these sheaves and the different meanings of Euler characteristics. And we'll see, this will give us a relation between, will allow us, okay, basically let's move forward a little bit. So I don't know how to handle H1 directly, but I have ways to find H0 XM directly. And now I need to figure out, then I need to go from H0 XM to H1 XM. So I need to set up a strategy to do that. Well, I know they are related because the sum is equal to this local Euler characteristic, but that's not, we need to know now something about Euler, the local Euler characteristic. Okay, so first thing, where do these local Euler characteristics appear? Well, they appear when you relate the holomorphic Euler characteristic of the reflexive symmetric power of the Cotangent bundle on the singular surface with the holomorphic Euler characteristic of the symmetric powers of the Cotangent bundle on the resolution. And exactly the difference is contribution coming from each singularity, and you have to, what is involved exactly is the local Euler characteristic above. All right, that's good. That's but that's not enough for us to work. We now need a relation between the holomorphic Euler characteristic and the kind of topological Euler characteristic of the sheaf. It's obtained by this topological expression. We know, okay, in the smooth case, they are the same. The holomorphic Euler characteristic is expressed by this topological expression, but on orbifolds, with singular varieties, that's no longer true. As we know, when you want Riemann rocks for a general case, you have singularities on the sheaf and you have singularities on the variety. So here you have mild singularities on the variety, so orbifold singularities, or singularities. We also have mild singularities on the sheaves because these are not locally free sheaves. These are orbifold vector bundles. They are reflexive sheaves. So, and well, there's still a topological expression coming from the same topological expression that you have for smooth case. It uses orbifold Shannon classes, not the usual Shannon classes, but these Shannon classes are defined in the same way. I mean, you can do it, express it using the same Grothendieck flow. But there's many ways to express these orbifold Shannon classes. And I call that expression the topological Euler characteristic of the sheaf. And so there is a relation. So the holomorphic Euler characteristic is equal to the topological Euler characteristic, sometimes it's called orbifold, but plus some local contribution from the singularities. All right, and there has been studied these local contributions from singularities have been studied. There's a formula for it. Representation theoretical formula for these contributions. I'll say something later about what we know about is the asymptotic behavior of these as m goes to infinity. And then there's another important relation, which is how do I relate the topological Euler characteristic of, which by the way, it is the holomorphic Euler characteristic for x tilde and the resolution because x tilde is smooth. How do I relate the topological Euler characteristic in x tilde with the topological characteristic in x in the singular variety? And the relation, there's a contribution from singularities where I'm looking at the local topological Euler characteristics for each singularity. All right. So these are the relations. These are the several relations between the natural Euler characteristics that you can associate with the sheaf, with these sheaves. And from that, we get this relation. You know, the mu is equal to the local topological characteristic plus the local Euler characteristic. All right. So if you do asymptotics, correct? I want to do the asymptotics. I want to understand the asymptotics. To do the asymptotics, the first important result is that the mu component is 0. So as m goes to infinity, you know, mu only grows like m square max, right? So it's if m cube is 0, that's a key result. This result is a result from Wall, Langer, and Blake. I guess this some people prove it in different ways. Another asymptotic behavior. So I talk about the asymptotic behavior of this piece. Now I'll talk about the asymptotic behavior of this piece. Well, this piece, the local topological Euler characteristic has the same expression as the global topological Euler characteristic, but instead of using the global Scher numbers, you use the local, I guess, orbifold Scher numbers, and so the expression, so this asymptotic piece still has the same expression as before. It's the second number, but it's the local second number divided by C factorial, and it's because this same expression. You have local orbifold local Scher numbers, and important to us, I mean, is that we actually have formulas for these numbers. So the second local Scher number of a quotient singularity is the Euler characteristic, topological characteristic of the exceptional locus, minus 1 over the order of the local fundamental group. And also important for us because canonical models have canonical singularities. Canonical singularities have that the Scher number C1 square is equal to 0. Okay, this is important. So we know very well the asymptotics of this and this. Therefore, we know the asymptotics of this. But we are interested in the asymptotics not of this, in a sense, but asymptotics of H1. So clearly we have that the sum. I know the asymptotics of the sum. We want to find the asymptotics of this part, and we'll know using the asymptotics of this part. That's the point. So now we have the relation between the asymptotics of H0 and H1 known, and now we can flow. An important thing that plays a role behind the scenes to some level, it's good to know, it's a general result that if I have a general of a canonical surface singularity, I always have that H0 XM is less or equal than H1 XM. In fact, it's less. And for AN singularities, these ones we have a full understanding, it's smaller, much smaller. For example, as M increases, the H1 becomes much larger. Okay, I mean, what I would say is kind of, there's no notation here, is that, I mean, if we'll see, it comes next, it's next page. So, okay, important, you know, because we're going to compare, I don't know, if time permits, we're going to compare two criterions. So we are going to propose, no, we're going to not propose, we're going to state a criterion for bigness of the Cotangent bundle on a surface general type. There is only another criterion written apart from the criterion I already stated at the beginning. These are like well-known criterions. I mean, the other criterion, recent criterion, is a criterion from 2014 by Rouseau and Rolleau. It's a criterion for about bigness of surface of general type, Cotangent bundle of surface of general type, and this criterion is based on a duality argument from my paper with Fedia. and I'll mention later on. But that criterion is weaker, much weaker than the criterion we're going to state later on. And that criterion uses this quantity as a when they want to understand or estimate the local asymptotic H1, the local component, they're going to use this quantity, while we're going to use this quantity. And this is bigger or equal to some. So it means that our criterion is, by this proposition or this result, is definitely at least equal, but for AN singularities, it's much stronger. I mean, this. Anyway, for AN singularities, we know everything, meaning we know how to calculate all the H0s, XMs, and we know the asymptotic behavior of it. We know that certain limit exists. We know what happens. Okay, let's don't have that much time. I'm going to do this. Hopefully this allows. I'm going to put serum A. So we now are in just trying to understand germs of canonical singularities of type AN. And so we would like to understand how this behaves as M increases. Well, I mean, the behavior of H0 as M increases is not given by a single polynomial of degree 3 most. It will be, degree 3 will be at most, but there's not a single polynomial giving this describing the evolution of the H0s. What there is a finite collection of such polynomials that describe the evolution of H0 with respect to M, where we allow M, where M varies in a specific congruence class. For example, for A1s, this is done in a paper of Alvarado, Niels Bruno, and Thomas, the student of Fedia. They show that there are 6 congruence classes to be considered for 6 polynomials that you should consider. We show that there's always a finite amount of congruence classes to consider. We calculate as I don't remember I think for H3 there are on the 36 different congruence classes. So I think A2 is still 6, but A3 is 36. I mean, and you can obtain formulas if you want to, but I'm not interested in that. What I'm interested in is understanding this leading coefficient. Notice here that so we have the R can change. These are different congruence classes. So the coefficients for the term in M and the constant term are depend on the congruence class you consider, but the leading coefficient, this one and this one, do not depend on the congruence class. So they are constant. They are uniform. It's interesting that the second one is 3 times the first one, but we don't use this. But the important is that so there is an asymptotic. So there is a limit. This limit exists. It's AN, and that's what we're interested in. This limit AN. And there's a formula for this limit. I don't say it here. You're going to be expressing directly below. And also another interesting thing to know is that this limit. So this asymptotic H0 piece, as N increases, it's bounded. It's always bounded by this number. All right, but we know how to relate H0 with H1, and so here's the result for really what we care about. We now have the formula for the local H1 coming from a AN singularity. And the formula is this one here. So close formula for these invariants. We notice, for example, while the limit of as n goes, so if I consider n singularity as the n of the n singularity goes to infinity, the limit of the asymptotic H0 remains bounded, but the limit of the asymptotic H1, local asymptotic H1, goes to infinity. So for n singularities, when n very large, the big part, like H1 is much larger than H0. It becomes the full component of the second number divided by 3 factorial. Another important remark that is important for some considerations later, but we're not going to use it when we want to use Parchenko bounds on the number of singularities. This is very important that we have this inequality, this understanding the relation between H1 and N. Okay, so this is I mean, there could be a talk to try to obtain these local asymptotic H1. Of course, it will be a challenging talk to do because it's several technical remarks. Okay, but we know this, so we know this local contribution. Okay. Okay, there's a question: is do I have these inequalities for all canonical singularities? If you have them, it'll be nice because it allows us to use Parchenko bounds to say something later on. All right. Now we have to think about time. I think well, maybe if the talk, the writing of the talk might become available, so you can see this theorem. So the motor of these, one of the motors. Okay, the motors of our work are twofold. One, of course, is calculating that local invariant H1 is essential for several of our remarks that come later on, and it's extremely convoluted to find those invariants that I just showed you in the previous page. And then the other big element is stating a criterion for bigness of the Cotangent bundle, because and also this criterion makes clear the nature of having a big Cotangent bundle. This result here is in some sense the technical. It's the result that allows to formulate the criterion that will be written down next time. And this is the proof, but in times wise, I don't know how I can do this. So let's just state, and if there's questions, I'll go through the proof. So say I have a surface general type, and I know that surface is the minimum resolution of a surface with quotient singularities. Then I have this criterion for bigness. So I know that this is in a sense, this gives me information about. I mean, this is less or equal than the local H1 of this, the local asymptotic H1 of X. So if this contribution of local H1s adding to the second number divided by 3 factorial is bigger than 0, then my cotangent bundle is big. In a sense, you could also say that it's less or equal if you don't. I mean, it's like this, and this, of course, is less or equal than what you call the asymptotic H1. I know by the full criterion of bigness, I know if the sum of these two is bigger than 0, then it's the cotangent bundle is big. And this is just having a lower bound. What this result is saying that I can find a lower bound for the asymptotic H1 by looking at the local contributions, local asymptotic H1 contributions from all singularities. That's what the nature of this. And to do this, it's I don't know, say like part of it's use low spectral sequence, use the vanishing of Bogdanov's vanishing. When you do this, you get this relation between H1, the global H1 on X, and you have now this piece here. This piece here is what we're going to call the non-local H1 omega X. And then we have here this contribution here. This comes from just the low spectral sequence. This is the local, so that's local H1 omega X. And then we have this element here that you have to deal with. So we like this to be like this. And we have a total understanding. I mean, I guess local H1 means the asymptotics of these, and asymptotics of these gives me this local. I talk about asymptotics. So I would like this H2 to go away, vanish of H2. And I mean, in the paper with Fede, we did a very sophisticated argument. Then in the paper of Rouseau-Rolleau, they observed that this could follow from stability of the cotangent of the tangent bundle of the singular surfaces. The surface is a canonical model, so a canonical bundle example, but just stated, not. And so great part of this result is to analyze why this is zero. And we do this. And for doing this, we have to use stability of the tangent bundle of here is more general than the case of canonical models. These are, in a sense, canonical models associated to. So canonical model is you have a surface of general type, smooth surface of general type. It has a canonical model situated, and it has canonical singularities. But if you start with a surface which is singular, we can still do the same process of trying to obtain from that surface a surface have a bilateral morphism to a surface where the canonical class is ample. And Kaumata has done that and shows that there is such a surface. The surface now doesn't have canonical singularities. It has still quotient singularities. You cannot do something do this, and we use then some result of Ganancia about from 2016 about smoothability relative to the canonical bundle of these sheaves, and from that we show the vanishing. It will be in the notes of the talk. It's here, but I have to. Time doesn't allow. Let's jump over here. It's one of. Okay, so now what I'm going to do is I'm basically do a corollary of the theorem of since we call one of the main theorems, and you get the canonical model singularity criterion, which is if I have a surface of general type, then I can figure out if the cotangent bundle is big if the following things hold. I have a local contribution for H1 coming from the canonical singularities. Now add it to the topological information, that second number of the X minimum, so the minimum model of X divided by 3. If the sum is bigger than 0, then the cotangent bundle is big. So this is really the local H1 omega X. I mean, or at least it's, yeah. The way it's defined is actually, it's going to be equal in the future, but now I just know that it's less or equal sense. It's equal for AN singularities. If the canonical model has only AN singularities, then you have equality here. So this is just, that's the kind of, so we now have a complete understanding of what's the local piece of the asymptotic H1. This comes from the canonical singularities of the canonical model of your surface. Okay, so localized. The non-localized is the sorry, I need to do something here. It's this piece here. And by the way, little is known about this part. This will involve. So the good thing about this criterion, one of the things about this criterion is it's an easy one to use, because we have a topological information in the sense of my variety, and that's many times known. If then it's a question of, do you know similarities? So it's local information about your variety. Do you know the similarities you have on the canonical model? If you know, I mean, since local information, you can calculate this component here. So these two terms are topological and local. So they are easy to attain in a sense from a variety. What's not easy to understand is, because it's global arguments, is the non-local piece. And in fact, this criterion is using the fact, well, I don't use it. I don't use the non-local. I assume it's zero. No, I don't assume it's zero. I don't assume it's not zero. Okay, so the result follows from all our previous work is that the asymptotic H1 is the sum of the local component and the non-local component. The way we define it is exactly equal for if canonical model has only n singularities. And the conjecture plus so I guess is the conjecture is that this equality is true for all axes. Meaning, to prove this conjecture, you just have to prove that the limits of of H1 as m goes to infinity for any canonical similarity exists. So you can use limit. Okay, so let's do some comparative analysis. So important thing is when we have a new criterion is compared with the existing criterion. What's the difference? So in 2014, Rouseau and Rolleau proved the following criteria. So if I several general type, I'm writing it in the same in a way that we can they state it in a slightly different way with language of orbifolds from a different perspective, but it boils down to this simple fact that the subset of general type will have big Cotangent bundle. When I add, you could divide this by 3 factorial and 3 factorial to get a sense like us, but you can take it away. If the sum of the second orbifold number of x canonical, so x canonical is a surface with quotient singularities, so there is this Chern number, this orbifold Chern number. And so I can calculate it, and I add that Chern number to the second number of x minimum. If it's bigger than 0, then the Cotangent bundle is big. But if you write it down more careful, what this means is just this. It looks similar to our criterion. Yes, this part here, of course, and this now is what they use to bound from below the local component of the asymptotic H1. It's this part here. So they don't use. We use H1 omega x bar, and they use this. But remember, from a conclusion after a proposition or a result we proved before, I know that this number is always bigger or equal than this. So our criterion is better always than this criterion. But of course, bigger or equals, if it's close, very close, it will be a mild change. But no, it's a huge difference for many similarities. It's way bigger. In fact, can be as maybe I have it here. So So I know that what we use in our criterion is bigger than what's used in Rouseau-Rolleau criterion. You know, if you want to compare, it can go up to being twice better. It starts by being, 60 better by this factor, and at the end better by factor of 2. But factor of 2 is going to see as a huge impact. Okay, so let's see the impact. So if I want to use any of these criteria, there is Miocca's constraint on the number of singularities, or what singularities are allowed on a surface of general type. He has the following criteria. Say I have a normal surface with only canonical singularities. In fact, this criterion is for quotient singularities, but I write it for canonical singularities. It allows me to use these instead of the second number. So this is now for canonical singularities, stated for canonical singularities. So if I have a surface, a normal surface with only canonical singularities, and its minimum resolution is x tilde, and x tilde is general type. Then there is a bound since on the singularities. It tells me that I have this difference here. This is how far it is from the extreme line, C1 square equals to 3C2, some kind of like what we can spend in singularities. We have this amount to spend in singularities, and each singularity contributes, costs this amount. And so you can have only cannot pass the cost, cannot pass what we have. And so this is Miocca's constraint. Well, this Miocca constraint fits perfectly Rouseau-Rolleau criterion. Immediately tells us that Rouseau-Rolleau criterion cannot be applied to any surface of general type for which the ratio between C1 square and C2, is less than 3/5, which is good, but it's far away from the best slope. Oh, so maybe then I have a theorem that says in our case, and I'm not gonna, let's stay here for you have it in your, it's recorded, you can go and see this. Well, one thing I realized that our criterion allows slopes. The lowest slope you can do is 1/15. So what this means is that our criterion can be applied virtually, because it depends virtually, meaning the Miocca constraint does not prevent our criterion to be applied to some surface for which the ratio is 1/15. So 1/15 is 9 times better than 3/5, right? So just 9 times better. But you have here this diagram. It makes clear. So this diagram is the C2 C1 square plane, and there's the region where surface of general type can live, which is this region here. Go up here. So surface of general type live there. And well, we know that in this region here, the cotangent bundle is big immediately from the topological criteria. By the way, this describes pairs of C2 and C1 square for surface of general type, minimal surface of general type. Okay, remember this. Okay, so this is so this region bigness is guaranteed by the topological criterion. Then where do criterion necessarily fail? So if I'm in this region here, the criterion might tell me that these surface over here, surface with these shadow numbers, might. The criterion allows maybe to show that the surface has big cotangent model. It doesn't mean that if it's here, it has big cotangent model, but might have. But the criterion might apply. Well, where definitely you never be able to apply the criterion is for Rouseau-Rolleau criterion is in this region here, below the line with slope 3/5. All that region, so infinitely many like pairs are not allowed, and all pairs here are not allowed. Very far from the Horikawa lines. Well, but our criterion just doesn't work, necessarily doesn't work for surface in the red region. This tiny region, this finite region here. So only finitely many pairs necessarily, like our criterion is not enough, will never be enough to show bigness. But by the way, again, being in this region does not mean that the cotangent bundle is big. It just means that our criterion can potentially work if you, okay, well, let's see. Maybe, sorry. That was interesting. So this is an hour past. Oh, okay. We could stop here, but let's just do this because it's going to be quick. I mean, a motivation for our work at the beginning was a role of symmetric differentials. I mean, symmetric differentials cannot play a role in proving that smooth hypersurface in P3 satisfy the Green-Griffiths conjecture or hyperbolic. The reason is because there are no symmetric differentials. But in our paper, we realized that there are resolutions of novel hypersurfaces which have big cotangent bundle. Now, resolutions of novel hypersurfaces are deformation equivalent to smooth hypersurfaces. In fact, this is the result. So I'm here. I start saying a smooth hypersurface in P3. If you look at second number, it's negative. So they don't satisfy. These surfaces are minimal, and they are canonical models. Well, second number is negative. Therefore, well, cannot apply the topological criterion, and you can also not apply our criterion because the canonical bundle is ample. So there's nothing you can do there. But Brookman in 71 proved that actually, not only it's not big, there are no symmetric differentials. So the symmetric differentials cannot play any role in obtaining restrictions on rational curves, elliptic curves, or entire curves. Then there is the result of, be aware of Birscon simultaneous resolution of singularities. It says that minimal resolutions of hypersurface of degree D in P3 with only canonical singularities are deformation equivalent to smooth hypersurface of the same degree. Okay, so there's a family of smooth hypersurface specializing to this surface, which is a resolution of an hypersurface with of degree D with canonical singularities. All right, so then the question is, can I have big cotangent bundle on this surface? So this means, are there representatives in the deformation equivalence class of a smooth hypersurface of degree D with big cotangent bundle? This actually can have impact on proofs about hyperbolicity for every hypersurface, but we'll leave it for another time. So there was this question, and in we show that okay, the answer is yes. Bogomolov and Bogomolov myself proved yes. Okay, I guess I erased something here, but this doesn't appear here. The answer is yes. We can do that. But then the question is, how low can you go in degree? It's very important because many results about hyperbolicity for surfaces smooth hypersurface in P3 depend very much on degrees. So for high degrees, conjectures are proved, but as you go to low in degrees, the methods fail. That starts failing, and I think that so there are very few examples of smooth hypersurface in P3 of degree of low degrees, which are hyperbolic, Kobayashi hyperbolic. I think the lowest degree possible is degree. That's what there are examples of degree 6. There are very few examples for degree 6, For degree 5, which is the Holy Grail, there are no examples so far. There's supposed to be. So it's interesting to know how low is the degree for which there are surfaces which are deformation equivalent to hypersurface of degree D, which have big cotangent bundle. It would be nice to arrive to 5, which is the best possible. And can you arrive to 5? Well, what we show is you can arrive to 8. All right, you can arrive to 8. Okay, it says surface, but remember, the problem of arriving here, if I had more time to explain, it has to do with constructions. You need construction of surfaces, hypersurfaces with many singularities, and there are some constructions, but they're not. They are incomplete, and so these results depend very much on what constructions are out there. But we have constructions and we have bounds. Like Miyoke provides a bound for the number of singularities. Barchenko is a totally different type of bound, gives also bounds from the number of singularities you can have on a surface, on a singular hypersurface in P3 with canonical singularities. They use mixed odds theoretical components. So there is this thing about constructions and bounds. So constructions limit us to only be able to prove that the mean dm is bigger or than 8. But one interesting thing is that the theoretical bound of Miyoke will not prevent us to use the CMS criterion to achieve degree 5. So degree 5 actually is attainable if there was only the, if there's only the Miyoke constraint. But Miyoke constraint is not the best for a low degree. Here, the best constraint is Barchenko. And Barchenko bound actually does not prevent degree 6, but prevents degree 5. And in fact, we conjecture that Barchenko bound prevents our criterion, the canonical model singularity criterion, to obtain degree 5, no matter if the surface has only AN singularities or not, or all singularities. So degree 5 is probably not be able to be achieved with our methods, but doesn't mean it's not true. It means that if you want to prove it, we need the local piece, local asymptotic H1, and we need information about the non-local asymptotic H1. If we have information on that, we might able to get the jump necessary to obtain bigness. But without information about the non-local, it's not enough. That's what we prove, and that's it. That's the end. Are there any questions?
Hi, Bruno.
Hi. Hi, thank you. Okay, it's here for the future.
Can you hear me?
Yeah, now I can, but not before.
Oh, okay. Okay. Yeah. Thanks for the talk. That was great. So most of your computations focused on these cases of AN singularities. So I noticed my question was going to be about the other singularities. I noticed you wrote something in this conjecture about them, but can you say something about how? Yeah. Okay,
it's a good question. I mean, other singularities. I know to understand this, like, okay, so the personal experience, finding the formulas for AN singularities was kind of painful, long, to get the patterns to be able to, you can do A1 singularities is very easy. It's like afternoon exercise. A2 or A takes a bit of time because you have to understand, these resolutions, these minimal resolutions for A1 you can only consider one patch, but if you have A2 you have to consider two patches. If you have A3 you have to consider three patches to cover the full resolution, and you have to figure out the compatibility of these obstructions to extend the symmetric differentials and to get the pattern. So the pattern for these obstructions, it takes effort, understanding how to calculate the numbers of symmetric differentials don't extend in certain degrees. It requires us to create a three gradation of the model of symmetric differentials. It is quite complex procedure. All right. So actually, I asked my students, like, do you want to do, the n singularity? But they balked at it. I want to move a bit forward, but now because the picture became more clear that these things are, I don't know, kind of fundamental for some of these results to understand this local, localized H1. So for me, it will be just nice to know that certain limits exist so that I can state the result. That what the limits are is something else. Well, the problem is that the action, I mean, the other groups are not non-abelian. And the three gradation that we do that allows us to decompose, finding these dimensions of symmetric differentials that don't extend, we break it in pieces. And the action also being diagonal makes it very easy to calculate these different dimensions. With the n and the n, the actions are not, the group is not abelian. I mean, we have to be, the three gradations have to be, the gradations have to be different. It requires adapting our methods quite a bit. I mean, a lot of things happen because of exactly the action being diagonal, group being abelian, and everything was at the end beautiful. At the beginning, it didn't look beautiful. At the end, very easy to kind of get a closed formula, because before you didn't have closed formula. For the n and the n is going to be quite the n and the e case is going to be quite more convoluted. I'm actually curious. If I might find some partner with courage, and we go for it to calculate these events. But I've not calculated these events. I mean, that's the long. I think it's going to be technically much more challenging. I mean, I imagine that if you pick up D4, you probably can do D4. I mean, I don't know. Maybe also the E's, maybe. But maybe, I don't know. But then getting a formula that's independent of n, well, that works for all n, I don't know. I don't think it's, but who knows? It's a project. It's for maybe a partner or other students. But it's a good question. Thanks. Okay. Well, thank you for coming, and it's here. It's forever recorded. So take care, guys. Bye.
Bye.